Hello, this is Math Kimchi, and in this video I'll be implementing heaps and heap sort. So first of all, what is a heap? Um, a heap is a binary tree which is always complete, meaning that all of the nodes are to the top and left as much as possible. So you can see an example of a heap here. So this is the root node, and 3 and 4 are its children, and 5 and 4 are 3's children, and 6 is 4's child. And you can see that everything is to the left as possible. So something like this isn't possible because the 6 could go here, and that would make it more to the left. And also, there isn't anything missing in here. So if we got rid of these two, we can't just get rid of it like this, because then 5 would be able to get into this spot. And something about a heap is that all of the children must be less than or greater than the parents. And to know if it's less than or greater than, it depends on what type of heap it is. So for this video, I'll be implementing a min heap, meaning that the very top, the root, is always the minimum, and in this case the 2 is the smallest in this entire heap, and so it is at the most top. And you can see that 2 is less than 3 and 4, and 3 is also less than its children, which are 5 and 4, and 4 is less than 6. So basically, as you go up, it gets the value decreases. And yeah, this is very useful in things like priority queues, where you want to know what the smallest or biggest element is. And you can also arrange this in an array. So since heaps are always complete binary trees, you can just go from the top and kind of scan left to right. So you could represent this heap in an array where it would be 2, and then you go to the next line, so it's 3 and 4, then 5, 4, and 6. And from this you could get this. And now, why should we use a heap? Why should we arrange it in this certain way? Well, it makes it easier and faster to access the smallest or biggest element. And that's because the restrictions make it so that the top, the root, is always going to be the smallest. And if you wanted to delete 2 from this, you would replace it with the last element, and by last I mean at the most bottom and most right. So it would be 6, and I just get rid of this. And from this, I would look left and right and see which one is smaller. So 3 is going to be better to go up here than 4, because if 4 went up here and traded spots with 6, then the 3 and 4s would be out of place. So we can replace 3 and 4, or 3 and 6. And here we can also replace 6 with 4, because right now 6 is greater than both of its children, so we can say 4 and 6. But if this was in a situation where it was, for example, 3, then we wouldn't have to switch anything, because the rule would still be true that 3 is less than 5 and 4, and this 3 is also, I guess, less than or equal to its children, which are 3 and 4. And if this was like a 2, then well, actually it wouldn't have been true in the first place. So yeah, that case is one we don't have to worry about. And anyways, let's get started. First, create a constructor, and I guess we could have one that takes in an array, or yeah. And let's have the int. And actually, for now, yeah, I won't worry about that. And we can say that int array is a new or actually array list might be better for this case. Cool. And first of all, let's have let's see what we need to do with heaps. So first of all, we have to create a insert, and it takes in an int added value, and we also need a int peak, which actually that's gonna be pretty easy. I can just do it right now. See, should be something called first, or I can just do get 0. And also we could have a remove or pop, and this just returns what was previously at the top. Right, and a toString would be nice as well. Alright, so first of all, we should start with the insert, because it's going to be easy to test insert without pop than pop without insert. So we said yeah, let me bring back an example. So to 7 and 6, 8 and 9. All right. That's a little bit, but yeah, if this was our heap and we wanted to insert a new node, so let's say we didn't have that 9 and we wanted to insert a 3, then first of all we'd see that 3 and 7 were out of place, so we would replace those two, and we don't have to care about 7 and its children, 7 being incorrect relative to its children, because even if it did have children, then 7 would be less than its previous child, which was even less than its child, so the new child is guaranteed to be greater than 7, and that's good because now we only have to worry about the 3, and in this case it works nicely, but a case would be that if this was instead of 4, then we would have to switch the 3 and 4 again. And now let's just say we wanted to add another integer to this. Let's say, yeah, 1. Then we would first see that 1 and its parent was out of order, so we would switch these two, and we don't care about the 4 even if it did have children. We wouldn't care for the same reason we didn't care about the 7, and the 3 and 1 we'd see are also out of order, so we would switch those two, and bam, now it works. So hypothetically, if we wanted to add another integer, we could add, say, 2 to this, and we just add it to the next row, and we'd keep on switching up, and yeah, we just keep on I guess swimming up until it gets into the right place. I think that's how some people call it, swimming. So let's see, we could say dot and see what arrays have. Because to start, we want to add it to the very end. Maybe it's just this. Yeah. Dot add. What do you call it? Oh, added value. And then we could say have a method called swim up, takes it an index, and yeah, what this does is it's gonna looks at the value at index and its parent, and if it is out of place, they should be switched. Switches them, and then it calls swim up for the new index value previous parent index. All right, and swim is going to be pretty easy. We could have something called private void I could have said swap or switch, but both are fine. And upper and lower index and yeah, this is gonna be pretty easy, pretty simple, but I don't think it should check to see if it is out of place. Yeah, it's gonna be fine if we don't check for it. Actually, yeah, this might be better. Turn swap needed. I wanna see how they do it. Alright, so you just have to say return if the swap was needed in the first place. Right, so if int_array.get upper, so the upper should be less than or equal to the lower, at least their values, lower index. So if return false, already in place, and return true. But before that, we have to swap the two. So int temp get upper index index, and then here is gonna be dot lower. Alright, so I create a copy of the upper value, and then I set the upper spot with the lower. Oh, and also upper should be the parent and child. And yeah, I guess that might be confusing because it's gonna be something like 0 and 1, and in that case it's gonna look weird. But anyways, set. Alright. Alright, so the simple swap is done, so we can have, so first of all, it should check if index is already at the very top, index equals 0, at the very top already, return. Otherwise, we can say if swap index, oh, I guess we can have parent index equals divided by 2. I think, yeah, that's all we need, because this index is 0, this is 1, so 1 divided by 2, but this is gonna be 2, and we want to get 0 from 2, so I guess it should be division. Wait, what am I saying? Yeah, it might have to be -1 and then 2 and then over 2, but we'll see if that doesn't work. Parent index no, I guess I have to call parent index first. Yeah. Alright, so that should be working, and we can just do size -1. Alright, now we have to create a yeah, static. Wait, I think there's a, alright. New heap, and I guess we can have opposed to heap equals new and I'm just gonna type in a bunch of random numbers. I guess I'll just add a negative number as well. And for each, say heap dot insert I and system dot out dot heap. Inserted. All right. Let's see what happens. All right, so 5, that makes sense. Then 2, 5. And then 2, 5, 4. So 2, 5, 4. And then 8, 7. Oh wait, is this just... Alright. Wait. I'm gonna have a better 2-string. So string s equals s. And for length. What's the problem? Size. And s dot s plus equals I plus this. And we also need to return, and we want to return when it's a power of 2. So we can have something private boolean is power of that's a bad name, but int I if I equals 0 return false while equals divide equals 2, or yeah, return I equals 1. Wonder if that's all it takes. All right. If is power of 2, I, and then we can just add a new line. All right. Okay, well, that didn't work, which is weird. divided by 2. I don't know if that's gonna fix anything. Alright. Now I just want to see. Print. This should be true. False? Why though? Zero. Or maybe, is this gonna create an infinite loop? No. Kind of seems to be working. Let's see. Well, at least it's partially working now. Oh, nice. Nice. It's, it's still a bit off. Just gonna try random stuff until it works. Yes. Alright. I think I accidentally got it to work. Or did I? Oh wait, I have to do int array get. Alright, now it should work. Alright, so first of all, does this follow the rules? So 1 is less than, -1 is less than 0 and 2, 0 is less than 5 and 2, 5 is less than 8 and 9, 2 is less than 7, 2 is less than 4 and 4. So yeah, it works, which is good. And now we should have pop. I'm not gonna, yeah, I'll just start with pop then. So in order to remove a element from a heap, or just the root, I guess, you have to swap the first and last nodes. So I have to do 6 and 1, and obviously I'm just gonna get rid of that 1, and from that we have to do, it's called syncing down, and clearly 6 is in the wrong place because it's greater than 2 and 3. But which one of these do we swap up with? Well, we have to swap up with 2, because if 3 swaps with 6, then it's gonna be 3 and 6 here, and these two guys are fixed. But then we know that 6 and its children are not completely fixed, and also we create an unnecessary problem because now we have to worry about 3 and 2 as well. And instead we can take the lesser of the two children and swap 6 and 2. So if we have 2 and 6, it's guaranteed that 2 and 3 are not going to have any problems. And now all we have to worry about are 6 and its children. So we can once more find the lesser of the 2 children. So it would be 5 in this case. And so we can switch 6 and 5. And boom. It works. So for pop, we have to create an int I equals, I guess we can just use peak I. Set. Right. I guess I can just do peak and say if we can have something called private sync down index, and this would be the index of the parent. But first off, we should I guess we could have something called unchecked swap. There should be a J, not enough. And yeah, this is gonna make this easier as well. Alright, uncheck swap, and can I have uncheck swapped of 0 and int array dot size -1. Huh. I can't believe they don't have a a function to remove the very last element. But that's fine, we can just do a remove and int array dot size +1. Right, and from that we can do, so I can do int I equals, and boom, sync down 0, parent index. Alright, so can have first our base case would be if it's already at the bottom, bottom has one child. So it's gonna be more broad to check if it doesn't have, it's gonna be more broad to check if it has either 0 or 1 child. So we can say if int array dot size Alright, so we can check if it has the right child, because if it doesn't have a right child, then we're gonna need to go into special cases, and left, same thing, but after that we're gonna have to check for a right child. So yeah, right child's gonna be better because it tells us that it's not a standard thing, whereas if we only check for left child, then we wouldn't know for sure if it was a standard case or not. So 2 times print index +2. So this is the index of the right child, and if that is equal to or greater than int array dot size, then means there is only one child. So can do, yeah, then we can check if +1 int array dot size, then return no child done syncing, return, and check if swap required between parent and left child. Or actually, yeah. Swap swap, and then we can just return, and afterwards we can say that int smaller child index. Alright, first let's find what the smaller child is. So if int array dot get 2 times parent plus 1 is greater than int array dot get 2 times parent index plus 2, then the smaller child index is gonna be plus 2, else plus 1. Don't care if equal. Can be any. Alright, then we just do if swap smaller child index sink down and despite this being called smaller child index, when we call sync down of smaller child index, we're actually still looking at like in terms of the value, we're still looking at the same thing as when we first began. So if for some reason it was like 6 and 5, we're syncing 6 down, right? And when we do that, we're still looking at 6, despite 6's index being the previous child's index. And something similar applies for something similar also applies for swimming up. When we make something swim up, we are just constantly looking at one specific value or node. And I guess we can have something called heap sort, public static void heaps. Heap sort unsorted. Ooh. Oh. And I'm gonna have to change this. But for now, it doesn't matter. Sorted. Return sorted. Oh yeah, it doesn't want me to do that. Oh, I guess that was just because it doesn't matter. Cool. Now we can do while is empty. Return int array dot is empty. Heap equal new heap is empty. While not heap is empty. Sorted dot append insert is just that. Pop, and before that, all right, I guess heap should have a better way of initializing. So we can have public heap and integer sorted. We can say, yeah, and then just do for each insert integer. Let's see what the problem is. Oh, unsorted. What? Oh. All right. Can do heap sort unsorted. Sorted away array. And yeah, all we're doing with heap sort is we create a heap using the elements of the list, and from that we just continuously pop until the heap becomes empty, and hopefully this should return a sorted list. And let's see, 1 0 2 2 4 4 5 7 8 9, and that seems great because it is sorted, and I assume all the elements match. What if we add an even bigger I just added a bunch of random numbers, and hopefully it should still be pretty fast. Yeah, something of this size isn't gonna really test the speed of my program, but it does seem sorted. yeah, uh, all the numbers are sorted, so that's good news, and that means that uh, pop is working, and I guess we still haven't used peak at all. Yeah. Um, I mean, it's probably fine if we don't test peak. It's not that important anyways. But anyways, that was heaps and heap sort using a min heap, and heaps are just a cool data structure, and they're also pretty useful. And I hope you enjoyed watching this video. Thanks for watching. Bye.